So this is the second part of the very brief history of formation of Navier-Stokes equations and part of a video series on the Navier-Stokes equations. So we last left off on Truesdell writings on the contributions of Leonhard Euler, and they were for the Euler equations, which were for basically an inviscid flow that's compressible. And for practical engineers, like those who are actually trying to build bridges and maybe early other flow devices, irrigation, they weren't very practical still, even though they remain and be seen to be correct today. And they're still unsolved today, not like anything's changed since then. We probably need some really good ideas and breakthroughs to overcome those problems. And then we try to look at only very, very ideal situations where they could be used and apply them to our lives to make the world a better place. The engineers opposing the mathematicians and theorists were mostly using empirical formulas to do practical design, like, frictional effects and pipe flow. Now, Laplace tried to develop a molecular model that could explain the laws of physics through the molecular forces, and perhaps in the bigger picture, that's the correct way to go. But remember, not everybody believed in molecular theory or atoms, even through the late 1800s, and some even the early 1900s. And Laplace did this through like an analogy of Newtonian theory, because he studied and was a big fan of celestial mechanics. So the Laplacian physics was definitely pushed forward for many years by Laplace's own students. And this approach was definitely very advanced at the time, but it may not have been the one that prevailed. It's summarized by Truesdell this way, that there are two methods constructing a theory of elasticity or fluid dynamics. The first, used by Boschevich, Navier, Cauchy, and Poisson, and after long discredit, now again in favor among physicists, deduces macroscopic equations from special assumptions relative to the behavior of the supposed ultimate discrete entities comprising the medium. Navier in 1820 took a Lagrangian approach to the problem and examined vibrating plates and analyzed the continuous deformation of the plates as composed of isotropic stretching. After 1821, he developed the idea that the resorting forces appearing in elasticity could be modeled as a response to the change of distance between the molecules. And small deformations of these intermolecular forces would be proportional to the variation of distance. So these are very important early physical assumptions and observations as postulated by Navier. The next year, in 1822, after another year of work, he extended this idea and theory to hydrodynamics. And he stated the idea that resorting forces generated in the opposition to the change of distance between molecules. And the changes of these forces would be due to the differences of velocities between the molecules. These computations led him to introduce forces, not only which were done in the Euler equations of pressure gradient, but a new force here written as viscosity mu times basically del U plus nabla divergence of U. And you can see this form very much like in the Navier-Stokes equations today. But we need to relate the second coefficient of viscosity to the first still. Anyway, the second force of viscosity is generated by the motion of the fluid, and this is not like this internal stress gradient in the fluid, which is also existing in the fluid static problem all the time in fluids that aren't moving, and also in Euler's equations. In 1821, a French engineer constructed imaginary models both of solid bodies and for fluids by regarding them as nearly static assemblages of molecules. Mass points obeying certain intermolecular force laws. Forces of cohesion were regarded as arising from summation of multitudinous intermolecular actions. Such models were not new, having occurred in philosophical or qualitative speculations from millennia past. Navier's magnificent achievement was to put these notions in sufficiently concrete form that he could derive equations of motion from them. A number of people tried to extend and work along with Navier. One notable figure, which maybe should have his name attached to the equations, is Cauchy. And in 1822, the same year of Navier's work, he used his results to show that the internal force exerted on the surface of a fluid parcel was no longer perpendicular to the surface but contained a tangential component or part. So if you recall in the fluid parcel, we're talking about the tangential terms. He developed a theory of elastic bodies, introducing the notion of internal stress that would generate forces exerted on the surface of imaginary, isolated, small elements. This stress tensor helped to lead to the modern definitions of the internal stress of fluid or pressure, the Cauchy stress tensor. Written on it, Archimedes also accomplished basic works, perhaps his most famous one, in mechanics of floating bodies. Here again, he did not introduce the physical concept which is central to the subject matter, namely the concept of hydrostatic pressure. But in this case, Archimedes may be excused. Mechanics had great difficulties in conceptualizing the notion of pressure, although Stephen immediately mapped out the task of doing so, and everybody after him was pursuing it. Even Newton was not yet certain of it. In a sense, the clear-cut mathematization of the concept of pressure was arrived at only in the course of the 19th century, beginning with the works of, say, Cauchy on equations of motion for a continuous medium in general. In the 19th century, the mathematical image of pressure became a tensor, though a special one, and the actual formation of the concept of a tensor and a full realization of mathematical status took a long time to emerge. Cauchy showed that the tensor sigma should be symmetrical and studied a quadratic form and compared it to the form introduced by the strain tensor, that there should be some relation. In an isotropic fluid or body, the stress tensor would have the same principal axis as the strain tensor. Then, using Hooke's law on elastic deformations, he assumed that the tensors were proportional, a proportionality coefficient independent of the deformation. For hydrodynamics, he used Navier's equations, except that the new force was given as mu in this form, and compare it to the one I just showed on the previous pages, which is right here as mu. It's a good correction. Poisson fought with Navier and Cauchy and used the Laplacian molecular approach, and with Cauchy a strict molecular theory, and rederived Navier's equations with a more general force term. And this is what you'll see in the form today. Here, this lambda could be seen as the second coefficient of viscosity. I suppose that I should write these deltas like this. Excuse me. Back to Stokes, some 20 years later, he studied the steady flows and introduced the seminal notion of stability, which introduced the fact that mathematical possibility of a given motion did not imply its existence if the motion were unstable. I should note that Stokes studied instability extensively over many years, and there's a great historical description of Stokes' work in the book Flows, World of Flows. 3 years later, he derived his own modelization of elasticity in hydrodynamics, and he varied du, the velocity. He decomposed as du as the sum of partials into du of 1/2 of partial I uj plus partial I uj transpose, plus 1/2 of the difference. He showed that the antisymmetric part to an infinitesimal rotation can be written this way, from 5 to 4, is identified with the vorticity, which is the curl of the velocity. Then he could write this form as 6. The symmetric part is the symmetric tensor, and the shear pressure is given by the tensor where the axes are superimposed by the axis of the infinitesimal deformation, and the coefficients were determined as functions of the tensor epsilon. For the symmetric, or to have symmetry, he obtained that the stress tensor should be a combination of the strain tensor and that of the trace. This gives, after taking the divergence, an internal viscous force expressed this way, which should look very familiar to those who write down the Navier-Stokes equations today, with the first and second coefficient of viscosity. So Stokes then found what we mostly see as the Navier-Stokes equations today. Stokes' derivation is commented by Truesdell, as Stokes derived the same equations as Poisson, but in doing so put the theory on a sound and clear basis. As far as the theory goes in fluids, with linear viscous responses concerned, this was the final paper. The system of equations, Stokes investigated creeping flows, where the nonlinear term in the Navier-Stokes equations, u dot nabla u, is neglected. And in particular, he looked at pendulum flows for the purposes of more accurately predicting time. These equations and the solutions, if that linearization is made, can have certain analytical solutions because, well, they're linear. The boundary conditions on those are the velocity and the no-slip condition, which Navier and Poisson use a tangential slip condition. The Stokes law was formed for the resistance of a sphere on a pendulum in a fluid, and this gave physical reasons why the no-slip condition could be used instead of the slip condition as an original physical justification. And after all, the predictions agreed with the experiment.